In this video, we add an addendum to the last video that was done on this problem. The last problem, we were looking at section 15.5, problem number 8 from the homework. And we had made a small little mistake. The first time we were doing this problem, we forgot to distribute our minus sign and forgot to put in minus 4x squared. Instead, we had put in 2y squared. So we made a little algebra typo, so this video right here shows how to fix the mistake. Red is everywhere that a correction has been made. Okay, and we finally get down to the answer that we get -6. Okay, which is showing all the steps, which is what the computer got when we did a triple integral. You also got -6. Okay. This video, I also want to show a resolution to what is the significance of the number -6. And the thing I need to remind everyone about is that -6, when we do this triple integral, okay, of some function f, okay, of some function 1 dv over some region, that the answer you get here is, quote, like the net volume. That word net is very important here because sometimes the function that you're integrating can be above or below the z-axis. And this problem is really rather a sneaky little problem that I want to show what's going on here. I've created a plot of the region. Okay, so I've plotted according to the problem that we had, that our function z goes from this x squared plus 3y squared, a paraboloid on the bottom, to a paraboloid on the top. And that's what we were seeing in this problem in the picture, that I'm going to plot the be bigger than the paraboloid on the bottom and smaller than the paraboloid on the top, and put in all your other x's and y values. And when you do that, you can see here that the plot of the graphs is that there's a paraboloid on the top and a paraboloid at the bottom, but at some point they switch top and bottom. The blue graph here for a certain part of x and y is the top function. This blue part is above the orange. But if you get to the outside, you can see here that there's this curve right here where blue and orange switch. Okay? And the triangular region is what we were seeing as the integrating from x going from 0 to 3y and y going from 0 to 2. That's this triangular region. So over that triangular region, we're seeing that the functions, the z values switched top and bottom. The top and bottom changed. And therefore, if you're doing this problem and trying to make sense of the number -6 that you got, there are actually two regions that should be drawn. You should also plot the region where one of the paraboloids is on the bottom and top. Switch the z's. And what you see in that case is that the region that you're looking at is actually made of two pieces. There's a part over that triangle, right? There's your triangle region in the xy plane you're integrating over. It looks like a triangle. But the problem switched top and bottom. Okay? And then the question here is, what is the sum of these two volumes? And still the problem is rather tricky because we're seeing that okay, let's go here and plot this for different values of z. You can see that right here, that the region, we need to extend z down below a little bit more. Let me come up here and plot this from, say, z to -20. plot these pictures. What we're seeing, the graphs take a little while to come up, but you can see here that z equals 0 is this red plane. Part of these z values go below the z equals 0 axis. So we're getting some sort of concept of negative volume there. So when you're adding everything up, you have to take into account your positive and negative volume. And since this function goes negative, the net adding up the two volumes, you could possibly get a negative number. And that's what we are seeing in this, when we're doing this problem. You know, the graphs, like, you have to be very careful in plotting. But the double integral worked all that out. The double integral accumulated all of your positive and negative volumes. And what we're seeing here is over that triangle, we're getting a net volume, a net negative volume. Okay? That, so you have to make some sort of sense of what that means. But that's what we need to do to kind of make some sense of the pictures here. And, you know, probably important to remind everybody that this additional thinking that we're doing in this particular video was not necessary for the problem, because you were just asked in the problem at hand to just do the triple integral, right? There's nothing which says that the triple integral can't come out positive or negative, okay? If you want to interpret it as volume, we're going to have to be more careful about where the functions switch top and bottom, right? We're going to have to be very careful about dividing this region up into its pieces, and switches can happen depending on the region. So one thing you could see, one hint at what we're going to have to be very careful about, that page below, is the fact that one of the paraboloids, if you look at the two z values that were given, you were given z was equal to x squared plus 3y squared, and also z was given as 8 minus x squared minus y squared. So it is possible here that x squared plus 3y squared does in fact equal to these two paraboloids. This is the paraboloid that opens down, this is the paraboloid that opens up. They do intersect each other, okay? And they intersect in the equation 8 minus 2x squared minus 4y squared is equal to 0, otherwise known as 2x squared plus 4y squared is equal to 8, which is the equation of an ellipse. Okay, so you can see here that in the xy plane, when x is equal to 0, y will be equal to plus or minus the square root of 2. Okay, and when y is equal to 0, you get negative 2, positive 2. So our ellipse that you're looking at in this problem looks like this. And therefore, when we were integrating from x going from 0 to x is equal to 3y, and y going from 0 to y is equal square root of 2, there's your positive square root of 2. So here's y is equal to square root of 2. And here is the line x is equal to 3y. So you can see here that the region we were integrating over, part of it is outside. So here's the circle of intersection, or the ellipse, sorry, ellipse of intersection. And the region that we were integrating over in the xy plane, there's a part here that is outside of the region where they switch top and bottom. So that's why we have this division between the two problems. There's this little curve here. This is part of the ellipse. Okay, that's part of the ellipse. And on inside of that ellipse, one of the functions is on top and bottom. And once you get outside of that ellipse, the functions switch top and bottom. Okay, so that's a hint at some of the stuff we're going to have to be careful about going forward.